Hello and welcome to today's webinar. My name is Tyler Reid. I'm the Manufacturing Application Manager here at GoEngineer. And today I get to talk about SolidThinking Inspire. Inspire is one of my favorite products to use, and today's topic is covering motion analysis, which admittedly I don't have a lot of experience with, but the little experience that I do, it's been a blast to use. So I'm really excited to show it to you guys. So if you're unfamiliar with the Inspire product, let's give you a quick introduction. SolidThinking Inspire is an analysis-driven concept design tool. Essentially what that means is that instead of keeping your simulation and your iterations dependent on simulation results at the end of your design cycle, let's bring them to the front of the design cycle and allow the software to tell us where we need material based on different load conditions, manufacturing constraints, and the intended use of the part. Inspire is super flexible, it's very powerful, and it's extremely useful to use. As far as the simulation tools go, they're robust. It is meant to be a sort of simplified FEA simulation, but that doesn't mean we oversimplify the study to the point that it's unusable. As we dig deeper into the motion and some of the joints and bolt patterns, we have a lot of very precise and important factors that we can include in our study. It's flexible in that it allows manufacturing constraints. So it is a topology optimization tool, and it's not the only tool out there doing this. But it is the only tool that allows us to constrain the results based on our intended method of manufacturing. Topology optimization has been a topic that has come up a lot over the past year or two, and many of the conversations have started because of the adoption of additive manufacturing or 3D printing of production and use parts. Topology optimization has historically delivered very organic shapes, things that were kind of unmanufacturable. That's no longer the case now with 3D printing, but only a very, very, very small sector of the market is actually 3D printing end-use parts. Most people are still machining parts, casting parts, molding parts, and this is where Inspire differentiates itself. We can constrain the results to accommodate those methods of manufacturing. Another unique thing that it has going for it is its ability to solve for multiple load scenarios simultaneously. So in the model that you see pictured here, where it's a flywheel moving a bracket, you might have different load conditions. You could have load conditions that the flywheel is weighted differently, or the flywheel has different resistance, or the brackets are carrying a weight, or it's moving different directions. Those scenarios can be solved simultaneously and deliver one result that accommodates all anticipated scenarios. Inspire does a few different types of analysis. It does manufacturing analysis, so we can analyze a part for its casting ability, its stamping ability, and we can do motion analysis, which is the topic of today, which could be static or dynamic load conditions. I mentioned Inspire being a topology optimization tool. What does that mean? It's essentially optimizing the shapes of the parts based on design intent and application intent. Many times these results are impossible to manufacture, and that's why topology optimization is sometimes known as, the true design for additive manufacturing. The big takeaway here is that instead of an engineer or designer drawing a part, then creating an FEA analysis for it, assessing the results, and then making adjustments to the part, we're eliminating that first guess as to what the shape should be, and we're asking the engineer, create some critical geometry, mounting points, faces that loads might be pressing on, and design spaces, potential spaces for optimization, essentially the design envelope. Input your supports, your pressures, your forces, your thermal loads, your accelerations, etc., and let the software determine the load paths. This is going to give you the basic shape of your part, in an optimized fashion. This means you're going to design faster and smarter and lighter. You're going to be able to create parts that have the same factor as safety but are lighter, or you're going to be able to create parts that have the same strength that are lighter. Inspire optimizes for different characteristics. It can optimize for the maximum stiffness. You can target a mass. If you're trying to work around resonant frequencies, you can take those into account. And you can also optimize for wall thickness. The shape controls that I mentioned, you can have zero shape controls, which would deliver an organic shape suitable for additive manufacturing. You can do an extrusion shape, which would be suitable for machining. Or you can do single or double draw molding, which would be suitable for casting or metal injection molding or plastic injection molding. So that's sort of the introductory phase of the webinar, covering the basics of Inspire, what it is. Let's jump into the motion analysis. I'm going to go back and forth between PowerPoint and the software as we work through an example so you guys can get an idea of what it takes to set up and run a motion analysis and what sort of outputs we can take from it. The ultimate goal here is to have a system where the parts move relative to each other, but we want to optimize one of the parts or multiple parts. We're going to use the motion analysis to determine our load conditions on the optimized part, feed those results into the optimization, and achieve our goal. So the first step of doing a motion analysis is we have to cover the connections. Connections are going to include something called a ground. This would be an immovable part. Rigid groups, which are parts that act as one. They have no relative motion between them. And then joints. Joints connect parts in ways that are going to allow movement at the joint location. There are several different joint types: pins, hinges, ball and socket, and all of these restrict degrees of freedom in certain ways. Some of them translational, some of them rotational, some of them a combination. So let's jump over to our example part and we're going to cover the connections. So I have this example part loaded up into Inspire. It came in as a Parasolid file. Inspire will open native SolidWorks files and other native CAD files. You can also draw geometry directly within Inspire. It is a CAD tool, so you don't have to originate your part in a separate CAD tool. You can draw it within Inspire if you choose. This is an assembly, and the idea here is that we have a flywheel. We have a couple brackets that are connected with a pin, and then we have a shaft. And the shaft is going to be our ground, and the flywheel is going to move. So let's set up our connections. Along the top, I'm going to go over to the motion analysis page, and we're going to just step through these little icons. Now, as we progress through here, you'll see that these icons they're really nice. One icon can control several different options. For example, under structure and loads, one icon allows me to select and apply torques and forces and pressures and supports. They're smart icons. Okay, so we're going to start with the ground, and I'm going to select my shaft. That's all there is to it. That's going to be my immovable part. And then I'm going to select rigid groups, and I'm going to start selecting some parts that are not going to move relative to each other. Essentially this portion of the bracket, and then we have some bushings in there that are interacting with the shaft, but they are not moving relative to the bracket. So I'm going to create a new rigid group with those. Okay. Lastly, we're going to do our joints. Now, when I select the joints, Inspire is going to preview any potential places for joints. It picks up things like aligned holes and suggests types of joints that we might want. And in fact, I can set it to auto-assign joints. And when I do that in this case, along the left-hand side in our model browser, we can see the joints that it applied. It applied a pin down here at the bottom, attaching the flywheel to the bracket, a pin between the two brackets. Now it assigned a pin. I can change that. I can also add attributes to it. Pins can be grounded. They can allow sliding movement. They could be both grounded and sliding. Now, one area that it didn't select how I would like is this outer area, which is the connection between our two rigid bodies. It selected a cylindrical joint. I'm going to go ahead and lock that. I don't want movement within those joints. Now, since we're on the topic of joints, there's a couple of things I wanted to mention. If I highlight a pin, for example, over here on the left-hand side in the Property Manager, I'm going to get some attributes about that pin. I see the material. I can assign a material to the pin. I can add pretension to the pin. I can also enable optimization of the pin, and this would either auto-calculate allowable forces on the pin based on the size and the material, or if I know the maximum allowable axial force or shear force, I can type that in. If I don't want to worry about the optimization, I can just simply disable it. All of these different joint types are going to have the ability to add some additional info like that. Pretension and maximum axial and shear force. There's all the connections for this example. Now let's talk about forces. Forces can be applied in a handful of ways. We're going to step through them. The number one way is motors. Motors drive parts in a rotational manner, and motors can be defined in terms of angle, speed, acceleration, or torque. Actuators drive parts in a translational manner, and actuators can be defined in terms of displacement, velocity, acceleration, or force. All just depends on, again, your design intent, what info you know, how the actual situation is going to play out in real life. Some other types of forces, we can apply coil springs. These apply a translational spring or damper or a spring damper force along the line of sight between two parts. Torsion springs do the same, except they do it around the pivot axis between two parts. And we can also apply gravity. We can apply gravitational acceleration in any defined direction. So let's apply some forces. Jumping back to our model, notice we are just going down the line along the top here. In this model, we really only have two forces. We have a motor force and we have a gravitational force. So let's start with the motor. My first click is going to be the axis that the shaft is going to rotate around. And then my second click is where the motor will actually be mounted to. And I'm going to click the flywheel again. So the motor is going to appear on the flywheel. It's grounded to the flywheel. And I'm going to get my little micro dialog. And in my micro dialog, I can assign the driving parameter. In this case, I'm going to go for angle. And I'm going to do 360 degrees. So we're going to, within this motion study, we really only have to turn it around 360 degrees, because if it keeps going more than that, the forces are not going to change. Another thing I can do within my micro dialog is adjust the profiles. Now, before I do that, let's jump back over to the PowerPoint, and we're going to cover one more slide here, and that's the idea of profile functions. So motors and actuators can have a time component added to them, and that means that the parameter that we're driving can have a profile to it. It can be stepped up, it can step and then pause and then step. It can be a wave format, an oscillating function, swept sine, impulse, ramping. It can be an expression or table driven as well. So that's what I want to do in this example is for my motor, I want it to turn 360 degrees and I want it to ramp up. So I'm going to choose ramp. Now over here on the left-hand side, back into the property manager, I can start adjusting some of the constraints or parameters of my ramp function. My start time is at 0 seconds. My duration, I'm going to do 1 second. Jumping back to PowerPoint, one last thing that applies to motors and actuators is the idea of a controller. The controller is going to allow the user to target a desired value by means of a feedback control loop. It's not going to play a huge role in my simple scenario, but I am targeting a 360-degree rotation. If it had troubles getting there exactly, there's two controller types that are going to help me control the movement of my motor or my actuator. There's the conventional PID control scheme, and within that you have adjustable gains. Your proportional, your integral, and your derivative gains are all user definable. And then we also have the idea of a soft constraint. This is essentially a mathematical constraint with some violation allowed. It's a soft constraint. It has adjustable factors called proportional factors and derivative factors. Okay. Motors and actuators use these controllers by default, but they can be disabled. So jumping back over, that's this controller area in the property manager. Right now it's set to soft constraint. My proportional and derivative factors are here. I'm not going to adjust those, but talking back to the point that Inspire is a robust tool and is going to give you the structure to create believable and accurate simulations, this plays into that. Now, if I were presenting these results, I might be concerned about, maybe the type of motor that's showing. So I can make some adjustments to those. I can rotate the motor. I can also change the motor size to fit something realistic. This is more of a visual representation here. Okay, so I have a motor attached to my flywheel. It's going to complete my 360-degree rotation in 1 second. My next force, I'm not going to use an actuator or any spring dampers in this example, but I am going to apply gravity. So as I apply gravity, I can adjust the direction. I'm going to set this to be in the Y direction. And if I want to tilt it, I can also tilt it a certain amount as well. So it's 15 degrees from off the Y-axis. I am just using a standard 1G acceleration, but that is overridable as well. All right, that does it for the forces. Now we're set to run the motion analysis. So there's actually several different analyses we're going to run here, and we're going to run them in this order. First, we're going to analyze the motion. This is going to allow me to select the runtime, the frame count, whether or not this is a transient or a static motion analysis. I'll look at the results. I'll watch the animations. I can plot results from there. So let's jump in and do that. We're over here in the run area now, and I'm going to select my run settings. I'm going to tell it to run in 1 second. My output rate is going to be 30 frames per second. It's going to animate while solving. This is going to be a static event. My gravity is enabled. And we're going to let this run. And that's it. I'll run it again just to show you. Cool. So once that's closed, I can now start plotting results. Any object I select is going to give me some results to plot. So for example, if I were to plot, say, joint 3, which is my shaft, right now we're looking at the forces on the shaft. We see X, Y, Z forces. I can right-click and change what I'm plotting. I could go to a torque, displacement, velocity, angular velocity, etc. And I can also export these. If I choose a different component, say the motor, I can plot, in this case, the torque required. From 0 to 1 seconds, it's going to show me the maximum torque needed for this scenario. Now, I did talk about applying materials to the pins and the other joints. The same applies to all of my parts. I would be applying materials. Right now, they're all set to 304 stainless steel. I can plot the rotation angle desired versus actual, so it looks like it actually has no problem achieving the rotation angle that I ask it to. We can plot the speed, that's going to be constant. We can plot the force on the shaft and the torque. So this is the motion portion, and the idea here is that we are going to pick up peak values off our forces, off our connectors, and off our parts, and then we're going to feed those into the subsequent analyses. The next analysis that we would typically do is analyzing the part with an FEA study. We can do linear static studies, we can check for the normal modes, we can check for the buckling modes. This is usually done as a precursor to the shape optimization, just to make sure that, we actually have room to optimize the shape. If the first study fails, if the part fails, or it has a factor of safety below 1, then we might not be able to optimize the shape any further. So that's typically what we would do next. So this is analyzing the part. We're going to select one part to analyze. Now later on, I do want to optimize this shape, so that's the part we're going to analyze. We can adjust the element size. I'm going to make it a little bit more coarse here, just so we can speed through this. Now, it is loading the forces and torques from the motion study, and I can control how many loads are loading. So right now, that defaults to 5 of the peak loads per connection. I could do a certain number of evenly spaced samples. Remember, I ran it for 1 second, and I asked it to do 30 frames per second. So I have 31 time samples. I could tell it to take into account all of the time samples. Now, in general, especially for a situation like this, I really only need the peak loads, and I don't even have 5 peak loads. I could tell it to do 2. And we're going to let this run. Now, I am doing these studies in real time right now. Once we get to the shape optimization, I might run one study in real time, but I have several studies done up, so I want to show you the different results. Because once we start running the shape optimization, this is where we add symmetry planes, we add manufacturing constraints, and we can toy around with those to achieve different results. So it's normal to run multiple iterations of the shape optimization. So the results are in. We're going to go ahead and view those results. There wasn't a lot of force on this part, so I'm not expecting anything super exciting here. We see our factor of safety is quite high amongst the whole part. We can see the displacement, and we can plot any of these. So this would be maximum displacement. Our percent of yield, again, is going to be small. We can see what areas of the part are in tension and what areas of the part are in compression. We can view our max shear stress, our von Mises stresses, and our major principal stresses. Okay, so that's running the FEA analysis. The next analysis is the actual shape optimization. This is really what we were after the whole time. We want to optimize this part by either reducing the weight or increasing the factor of safety or avoiding resonant frequencies, etc. We ran the motion analysis to create and extract the load scenarios to feed into the shape optimization. Now, I'm going to be running Topology, which is shape optimization, but Inspire will also do topography optimization. It will do gauge thickness optimization, say for sheet metal, and it will actually do lattice optimization now with the newest version, 2017.3. More on lattice optimization in upcoming webinars. So let's walk through setting up a part optimization. I'm going to go ahead and create some shape controls. This is going to help it run quicker, and it's going to help me ensure I'm getting the shape I want. The first thing I'm going to do is create some symmetry planes. So when I click on a part, it's going to pull up my potential planes for symmetry. I'm going to go ahead and remove that one, but we're going to keep these two planes of symmetry. And then we're also going to do a manufacturing shape control. And I'm going to select split draw. And it's essentially saying it's going to draft in the two directions I have selected. If I didn't want any draft, I could choose extrusion. Okay. The next thing I have to do is actually tell Inspire which part I want to optimize. If it's not already evident, I need to set this as something called a design space. And this is now signaled as the space that we're trying to reduce material from. Now, after adding that, I'm going to have to run the motion analysis again. So luckily, it only takes a second. And then I'm going to run the shape optimization here. So we're going to select our space to optimize. We'll usually give it an optimization name. We're going to say we want topology optimization. Our objective in this case is going to be maximum stiffness. We have to tell it what percent volume to target, and the default is 30%, meaning we're going to target a 70% reduction in volume. Now, sometimes this is too much, sometimes it's too low, but it's a good starting point, and then we'll assess the results and we'll check to see, do we have to run this again in a different target? I am not going to make any adjustments to the frequency constraints. We are going to assign a thickness constraint. This is essentially our mesh control. We're going to make it a little bit coarser so that it runs quick. And again, we're loading results from the motion study, and we're going to let that run. So now while this is running, I do have another part file open. It's the same assembly that I ran through a few different results this morning. And so I want to show you the comparison of the results. Between the different studies, I made a couple changes. One study, I eliminated one of the symmetry planes. In another study, I changed the joints where the shaft meets our bracket, highlighted here. I changed those to ball and socket joints. All of those are going to change the results slightly. It is nice that I can run the simulation in real time during a live webinar. It really does take just a minute or two, especially for an initial analysis. If I wanted something very precise or a very smooth result, I would bump that mesh control or the minimum thickness down a little bit, and then the study times can go up to maybe 10 minutes or so, but for the most part, we keep them at under 10 to 15 minutes. All right, this is taking a little bit longer than I thought. I'm going to let it keep running. We'll check back on it in another minute or two, but let's jump over to my other assembly and start looking at some results. So I do have this one colored in white so that we can see the differences here. Now here is my bracket. The result of the study that we just selected is here. And what we're looking at is essentially the load paths of this part under those initial conditions where the shaft has just a cylindrical joint to it, so the part can only spin around this shaft. We had kind of the off-center gravity, but we had symmetry planes. Now there's a few things that we can do. So notice I I targeted 30%, and it's showing me 30% right now, and it was actually a pretty good guess. But that's not always the case. So we have a slider, and we kind of can reduce this, and we can get a feel for just how much material can we remove. And if we wanted to add more material to be safe, where would we best put that material? Now we can also run an analysis on these parts. So I can analyze these parts, and I can run the FEA analysis on my optimized results. So typically we'll run an FEA analysis pre-optimization just to make sure we're in the right ballpark. And then we'll run an optimization to verify our results. So while that is running, let's jump back over. And our initial study is done now, so we can view that. And we can see, lo and behold, the shape is the same. Exciting, right? Now let's jump back here. Now this result is available, and this is going to be our FEA analysis on our optimized shape. So if we wanted to see our tension and compression, we should be able to do that. Here's our tension and compression. Our factor of safety is still good. Very high factor of safety. Our max shear stress. Now I can animate any of these so that we can see how this is twisting. I can also do call-outs. I could say min and max points. And I could specify any point on the model as well. Right now I'm doing von Mises stress. So very cool. Now within this model, like I said, I went through and I made some changes. The next analysis that I ran, I changed this joint and this joint, the two joints on the front are connecting to the shaft, to ball sockets. And the results came out like this. So you can see we're with more movement available at the shaft, we see a weighting of the material toward the front, toward the shaft. That's kind of what we would expect. Another study I did is I eliminated one of the symmetry planes. And I think if you look at the result, you could probably anticipate which symmetry plane I eliminated. It's in the YZ direction. And we get an asymmetrical result because of the way my gravity acceleration was angled off of Y. Now, amongst all of these results, I can compare them. So we can see my three different results. I can look at the total mass amongst them all. I can see the compliance within each one. I can see the objectives within each one. So this is a very common workflow for you to kind of play around with the different studies and toy around with, different shape controls, different symmetry, and make a judgment as to what is your best option going forward. And then going forward, we can use the PolyNURBS tool to create organic type shapes within Inspire. I can output this into SolidWorks, and I can start doing more detailed design using this shape as a template. And then typically once I have my detailed design in SolidWorks, I might do some further FEA analysis that is potentially more in depth. So that's the SolidThinking Inspire product, and in particular the motion analysis tool. Very quick overview, but it should give you an idea of what goes into creating these, going through your connections, setting up your forces, running an motion analysis. Once you have the motion analysis, probing your results to find, your max force needed for your motor or your net max force for your actuator, so that maybe you can spec out those components. But then you take the motion analysis results and feed them into the shape optimization and start making design decisions based on those results. All of that together means you're going to start out with a better product. Overall, your design cycle is going to be faster, it's going to be smarter, and a better result overall. So I want to thank you guys for joining this live webinar. We're going to try to do one SolidThinking webinar a month, so we'd love for you guys to join all 12 months next year. And happy holidays, and take care.